Now we look at applying Unit 3, where we looked at work and energy to objects that are rotating. Specifically, we look at, in this unit, or excuse me, this specific lesson, rotational kinetic energy. If you recall, kinetic energy deals with objects that are in motion. Before, we looked at objects that were strictly in translational motion, so what we now call translational kinetic energy. But we also recognize now that objects can move in more than one way. Specifically, they can also move by rotating as well, which gives rise to rotational kinetic energy, the topic for 7.4. So rotational kinetic energy versus translational kinetic energy. So there are two forms of rotational kinetic energy, there are two forms of kinetic energy. This should just be strictly kinetic energy, not rotational kinetic energy. So there's kinetic energy due to an object's translational motion, which is the traditional K equals 1/2 mv squared. And then there's kinetic energy due to an object's rotation, which, you guessed it, the equation is exactly analogous to the equation for translational kinetic energy. So rotational kinetic energy is equal to 1/2 times the moment of inertia times our angular velocity squared. So it's the rotational analog of our translational kinetic energy, with mass replaced by the rotational form of mass, aka moment of inertia. And then right here we have our velocity squared replaced by angular velocity squared. All right. So units for rotational kinetic energy are the same as for energy, since both are, well, energy, joules. So conservation of energy and rolling without slipping, okay? So when an object is rolling down an incline like this, okay, and there's a force due to friction that's acting, causing our object to roll, okay, energy is still conserved in the system despite the presence of the force due to friction that makes our object roll. The reason being is that friction, even though the force due to friction is a non-conservative force and it does traditionally dissipate energy, there's a requirement that this force due to friction acts over a distance on our object in order to dissipate energy. If you recall, work is a change in energy. It takes energy out of the system, puts energy into the system. So the work done by friction not only requires a force due to friction, like we see right here, but also requires that force due to friction to act over a distance on our object. So what's happening right here is that friction acts at a singular, constantly changing point. Again, our wheel is constantly rotating. So the point of contact is always going to be changing on our wheel. So as a result, friction is not going to act over a distance, but rather at a single point, and it will not be able to do any work on the object. So as a result, the force due to friction will act right here, but it's not going to dissipate energy, and energy will be conserved in our system. So since kinetic energy of the object is broken up amongst translational and rotational kinetic energy, that means there's a trade-off in motions for a rolling object. Okay? So specifically, if we have a set amount of kinetic energy for an object, okay, then that kinetic energy can be split up amongst rotational kinetic energy and translational kinetic energy. And so as we'll explore and see in class with demonstrations and activities, is that if the rotational kinetic energy increases, then that means there's less kinetic energy available for translational motion, which means that our object will rotate faster, but it will move with a lesser translational velocity. So let's take a look at an example with a conservation of energy problem with rotational kinetic energy. So the problem-solving process is still the same as before, except now we have an additional term for rotational kinetic energy thrown in to our overall energy term, okay? So a 2 kilogram ball is rolling with a linear velocity of 5 meters per second when it comes into contact with a spring with a stiffness of 120 newtons per meter. How much will the ball spring system compress before coming to rest? Ooh, there should be a question mark there. Ooh, the English professor in me does not like that. The radius of the ball is 0.05 meters and the moment of inertia for a sphere is I equals 2/5 mr squared. All right. So again, we start off by writing down our knowns and unknowns and looking at what we're trying to solve here. All right, so we're rolling on a flat horizontal surface right here, so we can assume that there's no change in height, so we don't need to worry about gravitational potential energy at all, okay? If there is a change in height, we do have to worry about gravitational potential energy as we've seen so far. So our ball is rolling initially with a linear velocity of 5 meters per second. So we start out by writing V1 equals 5 meters per second, okay? A spring so our spring starts out unstretched. So we can say that X1 is equal to 0 meters. This should say 0 meters, not meters per second. So that's a typo on my end right there. So our spring is unstretched, so it's at its equilibrium position of 0 meters. And now at the second spot, we're now looking at our second spot of interest, which is when our spring is fully compressed, when the ball and spring is fully compressed. So when this happens, our final velocity is going to be 0, okay? The ball has come to complete rest. The spring is fully compressed. So for a brief moment, the spring and ball system is going to be at 0 meters per second before the spring starts decompressing. So our final velocity is going to be 0 meters per second. And our final position, the amount that by which our spring compresses, is our unknown x2. Okay? So we're going to have initial translational kinetic energy plus initial rotational kinetic energy plus the initial elastic energy of the potential energy of the spring, and that's going to be equal by conservation of energy to the final translational kinetic energy plus the final rotational kinetic energy plus the final elastic potential energy of the spring. So we can cross out the initial elastic potential energy of the spring because our spring is initially unstretched, so that's going to be 0. And we can cross out the final translational kinetic energy and the final rotational kinetic energy because, again, our ball, for a very brief moment before the spring starts decompressing, is going to be at rest, which means that the kinetic energy of the ball is going to be 0. So now we start substituting terms in. We're going to have 1/2 mv1 squared plus 1/2 I omega 1 squared equals 1/2 k times x2 squared, okay? So what we can take note of right here is each term contains 1/2 in this equation, so we can cancel out the 1/2s from both sides. And then what we can do with the I is we can replace I with 2/5 mr squared, our moment of inertia. And then because we all want to work in one single series of variables, either translational or rotational, what we're going to do is replace our angular velocity omega with v over r, if we recall our conversions from 7.1. So that way everything is going to be in terms of linear variables, specifically our linear velocity. Okay? So as a result, we're going to have mv1 squared plus 2/5 mr squared, the moment of inertia that we replaced I with, and then we're going to have v1 over r squared because, again, we replaced omega with v1 over r. And then this is all going to be equal to k times x2 squared. So right here we have an r squared, and then inside of the parentheses right here we're going to have divided by r and then squared, so we can cancel out the r squared terms on the top and bottom, which is going to leave us with mv1 squared plus 2/5 mv1 squared equals k times x2 squared. So using fractions and adding fractions together, we can combine mv1 squared and 2/5 mv1 squared, and that's going to give us 7/5 mv1 squared equals k x2 squared. Okay? So as a result, we can now solve for x2, which gives us square root of 7/5 mv1 squared divided by k, which as a result of plugging in all our knowns is going to give us 0.763 meters for the compression of our spring. So the problem solving process is the same as before, except the big step that we have to take note of right here is if we look at this line right here, we have to replace I with the equation for the moment of inertia, and in order to get linear variables, we have to replace omega with the linear variable conversion. Similarly, if we were looking for angular velocity, we would have to express v in terms of angular velocity. So we'd have to replace v with omega times r. Okay, so that's the only caveat that we have to make with these conservation of energy problems when considering rotational kinetic energy.